Welcome! Today, we're going to explore a powerful tool for analyzing data: semi-log plots. Exponential growth and decay are incredibly common in the world around us, from the spread of information online to the decay of radioactive substances. Our goal today is to equip you with a method to easily identify if an exponential model is appropriate for a dataset. By the end of this lesson, you will be able to: first, determine if an exponential model is appropriate for a dataset by examining a semi-log plot. And second, construct the linearization of exponential data. Before we dive into semi-log plots, let's take a quick moment to refresh our understanding of exponential functions. The general form of an exponential function is y equals a times b to the power of x. Here, a represents the initial value, or the value of y when x is 0, b is the constant ratio or growth/decay factor, and x is our independent variable, usually representing time. This constant ratio is the key characteristic of exponential functions. It means that y changes by the same multiplicative factor b for every unit increase in x. This is in stark contrast to linear functions, which have a constant additive change, or a constant slope. Consider the difference. A linear function adds the same number every time, while an exponential function multiplies by the same number. Let's look at a table. In this table, the linear function y equals 3x plus 2 increases by adding 3 for each step in x. The exponential function y equals 2 times 1.5 to the power of x multiplies by 1.5 for each step in x. This is the fundamental difference. So, how do we spot this constant ratio b if we just have a cloud of data points on a graph? On a standard graph, an exponential function looks curved. It starts out slow and then rises or falls very steeply. It can be hard to tell if this curve is truly exponential or some other type of polynomial function. This is where semi-log plots come in. Our goal is to transform this curve into something that's easy to identify, like a straight line. A semi-log plot is a special type of graph where one axis is scaled linearly, just like a normal graph, but the other axis is scaled logarithmically. Most commonly, the y-axis is logarithmic, and the x-axis remains linear. A key feature of a semi-log plot is that any dataset following an exponential pattern will appear as a straight line. Let's demonstrate this. Here is the same exponential curve, but now plotted on a semi-log graph. The result is remarkable. The curve we saw before is now perfectly straight. This transformation makes it incredibly easy to see if a dataset is exponential. You just have to look for a straight line. So, why does this happen? The answer lies in the properties of logarithms. Let's see the algebraic transformation that makes a semi-log plot work. We start with the general exponential equation, y equals a times b to the x. Now, we'll take the logarithm of both sides. It doesn't matter what base we use for the logarithm, as long as it's consistent. Let's use base n. Using the logarithm property, that the log of a product is the sum of the logs, we can separate the right side into two terms: log base n of a plus log base n of b to the x. Now, we can use another logarithm property, the log of a power. This allows us to bring the exponent x down as a multiplier, so we get log base n of a plus x times log base n of b. Let's rearrange this to look more familiar. We can write it as log base n of y equals log base n of b times x plus log base n of a. This is the key. Look closely at this equation. Does it resemble any form you know? It's the equation of a straight line. We can compare it to the standard linear form, y equals m times x plus c. On our semi-log plot, our vertical axis is representing log base n of y. Our horizontal axis is representing x. This equation confirms that the relationship between log and x is linear. The result is a straight line. Because the transformed data forms a straight line, we can now apply all of our familiar tools for working with linear functions. By finding the slope and the y-intercept of the line on the semi-log plot, we can actually find the parameters a and b of the original exponential model. Let's review our linearized equation. Remember, it's the equation of the line we see on the semi-log plot. The slope, m, of this line is the coefficient of x, which is log base n of b. The y-intercept, c, is the constant term, which is log base n of a. This gives us a direct connection. The slope of the line on the semi-log plot is the logarithm of the original exponential function's growth factor, b, and the y-intercept is the logarithm of the original function's initial value, a. So, if we have a straight line on our plot, we can find its slope and intercept. and then use them to reconstruct the original exponential equation, y equals a times b to the x. All the techniques for linear modeling, like finding the slope between 2 points or using linear regression, can be applied. An important advantage of this method is that we never had to add a constant to our y values. Unlike other linearization techniques, the logarithmic scaling does all the work for us, naturally revealing the exponential behavior. Let's work through an example to solidify these concepts. Suppose we have a dataset that we suspect is exponential. Let's create a semi-log plot to confirm our hypothesis and find the model. We have these data points. Let's see if they are best modeled by a linear or exponential function. First, we'll plot them on a standard graph. As you can see, the points on a standard graph form a curve that is clearly not a straight line. This suggests that a linear model would be a poor fit. Let's now create a semi-log plot. To do this, we'll keep the x values as they are, but we'll take the logarithm of the y values. Let's use base 10, so n equals 10. We calculate the log base 10 of each y value to create a new dataset. These are the values we will plot on a standard graph. Now, we plot the x values against their corresponding log y values. And look, the points now fall on a perfect straight line. This confirms that the original data is indeed exponential. We've confirmed the data is exponential. Now, let's use the line to find the exponential model. We need to find the slope and the y-intercept of this line. Let's use 2 points, 0, 0.602, and 1, 1.079. The slope m is the change in the y values divided by the change in the x values. This gives us a slope of approximately 0.477. The y-intercept, c, is the y value when x is 0, which is 0.602. Now we can connect these back to our exponential model. Remember our formulas. The intercept c is log base n of a. So, we have 0.602 equals log base 10 of a. To find a, we convert this logarithmic equation into its exponential form. A equals 10 to the power of 0.602, which is approximately 4. The slope m is log base n of b. So, 0.477 equals log base 10 of b. Converting to exponential form, b equals 10 to the power of 0.477, which is approximately 3. We found our parameters. The initial value a is 4, and the growth factor b is 3. We can now write the exponential model for our data, y equals 4 times 3 to the power of x. And this perfectly matches our original data set. This shows how powerful this method is. Let's quickly review what we've learned, and then pose an exit question for you to consider. Today, we've seen how semi-log plots can be used to identify exponential relationships and build exponential models. Semi-log plots linearize exponential data. This is due to the property log of a times b to the x equals log of a plus x times log of b. On a semi-log plot, the slope is the log of the growth factor, and the y-intercept is the log of the initial value. This allows us to use linear regression to model exponential data. The key idea is this. An exponential function becomes a linear function when you graph it with a logarithmic scale on the y-axis. This transformation allows us to use simple linear tools to analyze complex exponential behavior. Now, for your exit question, how can you determine, just by looking at a semi-log plot, whether an exponential model is appropriate for a dataset? Take a moment to think about it. The answer is simpler than you might think. The answer is straightforward. If the data points form an approximately straight line on the semi-log plot, then an exponential model is appropriate. The straighter the line, the better the fit. This is the visual test that semi-log plots provide. Thank you for watching. I hope you now feel more confident in your ability to work with exponential data using semi-log plots. Hello, I hope you found that lecture on semi-log plots helpful. If you'd like more resources, there are several options we can create for you. We can generate a student fill-in guided notes version to help you follow along during the next lecture. We can also provide a practice problem set with an answer key, complete with AP-style multiple choice questions, so you can test your understanding. And if you want a quick check of your learning, we can create a short formative assessment quiz. Just let us know what you would prefer. We're here to support your learning. And as always, you can download a PDF of the full lecture notes from the link provided.